let's consider the integers as my group, and I want to consider the normal subgroup, that is the cyclic group generated by 6. So I want to consider Z mod, the group generated by 6. So let's think about what these elements actually look like. Well, they're the cosets. So I could have 6 plus 0. That's negative 18, negative 12, negative 6, 0, 6, 12, 18, etc. I could have the group generated by 6 plus 1. So negative 17, negative 11, negative 5, 1, 7, 13, 19, etc. The subgroup plus 2. Negative 16, negative 10, negative 4, 2, 8, 14, 20, etc. 6 plus 3. This is minus 15, minus 9, minus 3, 3, 9, 15, 21, etc. We could add 4. Now we have negative 14, negative 8, negative 2, 4, 10, 16, 22, etc. The subgroup of 6 generated, or subgroup of generated by 6 plus 5, this would be minus 13, minus 7, minus 1, 5, 11, 17, 23, etc. And if we try to add 6, we would get back to where we started and we would just cycle through. These are all of the possible subgroups. Since I don't want to write down these really long cosets every time I want to deal with them, let's look at an abbreviation, some kind of notation to denote these to make them a little bit easier. So I'm going to denote each coset by the number I added with a bar over it. This shows me that 1, I can reference the number that I'm adding to easily determine which coset I'm talking about. The bar is just kind of a shorthand quick notation we can do to remember that we are talking about cosets instead of just these normal numbers. So that tells me that Z mod, the subgroup generated by 6, consists of 6 elements: 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, and 5 bar. And not only that, I can actually build a group table to go along with these. As I'm building this, adding 0 is my identity. So that doesn't change anything, and I can go ahead and fill in both that row and that column pretty easily. And then I have to remember the way these cosets work. 1 plus 1 means I just add the elements that I'm adding. I'm adding the subgroup generated by 6 plus 1, and then the subgroup generated by 6 plus 1, I just add those 1s to get 2. 1 and 2 would give me 3, 1 and 3 gives 4, 1 and 4 gives 5, and then 1 and 6. The subgroup generated by 6 plus 6 is the same as the subgroup generated by 6 plus 0. 2 plus 1 is 3, 2 plus 2 is 4, 2 plus 3 is 5, 2 plus 4 is 6. We already said that's the same as adding 0. 2 plus 5 is 7, and that's going to be the same coset, the subgroup generated by 6 plus 7, the same as the subgroup generated by 6 plus 1. And we can continue this process. We would get 4, 5, 0, 1, 2 here. The next row would be 5, 0, 1, 2, 3, and then finally 0, 1, 2, 3, and 4. So something we may notice here is that if I were to just ignore all of these bars, take all of the bars away that indicated that we were talking about these cosets in the first place, then this would be the table for Z6. So what we're saying is that this Z mod subgroup generated by 6 is the exact same thing as Z6. In fact, the quotient group construction of Z mod subgroup generated by 6 is the rigorous way of constructing Z6. And in general, for any n, if we consider its quotient group, that's going to be isomorphic to Zn. So this is the very rigorous way of constructing our modular groups, and modular arithmetic is using this idea of cosets and the quotient groups of the integers. The motive for the quotient group construction and the way we do this is that it gives us a way to actually produce all of the homomorphic images of any group. However, what's even more fascinating is that in practical instances, we can often choose our subgroup H to factor out unwanted properties of G, preserve in G mod H only desirable traits.